Linear Algebra Part 6. In this part, we're going to talk about transformations. Now, we have already seen some of that previously, okay, some explanation and some examples concerning transformations. Here, we're going to go deeper and explain further what transformations are. Let's start with the definition of linear transformations. A linear transformation or linear map is a function between two vector spaces that preserves the structure of vector addition and scalar multiplication. Okay, so let V and W be vector spaces over the same field F, such as R or C. A function T, which is the transformation from V to W, is called a linear transformation if for all u v vectors existing in V space and all scalars C existing in F, which is the field, okay, you have these two characteristics. So first, the additivity, which means the preservation of addition. So the transformation of u plus V is equal to transformation of u plus the transformation of V. Second, homogeneity, which preserves scalar multiplication. So transformation of C times U, C being the scalar, is equal to C multiplying the transformation of U. Okay, so key properties: linear transformations always map the zero vector in V to the zero vector in W. This is one of the most important keys that we've seen before in the previous video at the end. Okay, where we have, like, we could have proven, okay, whether V and W are space and subspace, or like whether, sorry, V is a transform of W, because always the zero vector in the first maps to the zero vector in the second. The image of a linear transformation is a subspace of W, and the kernel, which is the set of all vectors mapped to 0, is a subspace of V. Remember that V is being transformed into W through the transformation. So examples: 1, let's say you have a transformation R2 defined by Txy equal to x 3y. Okay, this is linear because it respects addition and scalar multiplication, correct? Okay, so let's say you have x1, x2, and y1, y2. You end up with 2x1 plus 2x2, you know, and 3y1 plus 3y2. If x is equal to x1 plus x2, y equal y1 plus y2. And if you multiply by a scalar, okay, let's say 4, so 4x times 4y, okay, it's yeah, for x and y, sorry, equal to 0, the scalar multiplication would always give you 0 as well. That's the point. And for the addition, okay, so 2 times x1 plus x2, 3 times y1 plus y2. For x1, x2, y1, y2 equals 0, this will always send you to 0 as well. For both the scalar multiplication and the addition, it is closed. Why? Because for x and y equals 0, the scalar multiplication gives you 0. For x1, y1, x2, y2 equals 0, if you replace x by x1 plus x2, y by y1 plus y2, okay, this always sent you to 0. For the second example, T is the transformation from R2 to R2 defined by Txy is equal to x plus 1 y. Is this linear? No. And simply because if you replace x and y by 0, T0, 0 does not give us a 0 vector, but instead 1, 0, which is different than 0, 0. Hence, it's not linear. It does not send us back to 0. Okay? Now, another proof. Okay, so let's say we want to prove that the scalar multiplication is not respected. Okay, so if we multiply T by a scalar c which is different than 0. Okay, c can be 3, 4, 5, whatever number that you want. So c times x plus 1 y, okay, for x and y being equal to 0. So this gives us cx plus cy. Okay, now for x and y equal to 0, this cancels out, this becomes 0 as well. We are left with c0, which is different than 0. Hence, it is not linear. Okay, that's another reason for that. Now, does it respect addition? Okay, let's check the addition out. So, let's say you have two vectors, u with coordinates x1, y1, and v with coordinates x2, y2. Okay, so we simply replace dxy with, x with x1 plus x2 and y with y1 plus y2. Why? Because we are evaluating u plus v. Okay, you add the x together and the y together. So, okay, dxy becomes, instead of x, you place x1 plus x2 plus 1, correct? And on the other side, y, which is y1 plus y2. For x and y equal to 0, for x1, y1 equal to 0, and x2, y2 equal to 0, we get again, okay, so this is 0, but you still have 1 here, and y1 plus y2 is equal to 0, which is different than 0, 0. Hence, it is another proof, another solidification of the proof that this is not a linear transformation. A linear transformation T from V to W between finite dimensional vector spaces can be represented by a matrix once we choose bases for V and W. Now, the bases again, as we mentioned, these are the generator vectors, okay, that are not linear combinations of each other. They are linearly independent vectors. Okay. Now, case 1, standard bases, usually Rn and Rm. Suppose we have a transformation from Rn to Rm, okay, between two different dimensions. For example, from R3, dimension 3, to R2, dimension 2. And we want to find its matrix representation. You take the standard basis vectors in Rn, okay, so you have these standard vectors, and you place them, on top of each other to form the matrix. Okay, so you have E1, 1, 0, 0, etc., E2, En. You compute their images under T. So transform of E1, transform of E2, these are the different images. And you place these as column of a matrix A. Okay, so the images, you place them as column within the A matrix. TE1, TE2, etc. Then for any vector x within Rn, T of x is equal to A times x. Okay, so for any vector x within Rn, Tx is equal to Ax. Example, let T be a transformation from R2 to R2. Okay, Txy equal to x plus y and 3y. Okay, so first question, apply to the basis vectors. Second question, form the matrix using these as columns. You can pause the video, try to solve it first, then get back to check whether it's correct or not. Apply T to the basis vectors. Here we need to choose two basis vectors that are completely independent, linearly independent. Okay, what would those vectors be? So txy, okay, you choose x1, y0, and x0, y1, or the following vectors. Okay, so x1, y0, and x0, y1. These are two basis vectors. So let us replace them within T, respectively. T10 is equal to, you replace x by 1 and y by 0. So this becomes 2 here. Y is 0 and 3y is 0. What remains is 2, 0. Okay. T01, you replace x by 0 and y by 1. So you get, since we've replaced x by 0, y by 1, okay, so you get here 1 and 3, which is T01 equal 1, 3. Form the matrix using these as columns. So A is equal to 2, 0. Replace the first as the first column, and 1, 3 the second column. Thus, Txy is equal to A times x and y. Okay? Case 2, general basis. Okay, if V and W have non-standard bases, okay, base V is equal to V1, V2 all the way to Vn, and BW equal W1 all the way to Wm, then compute each transformation of Vj, express each result as a linear combination of Wi. Okay, so compute each transformation Tvj, express each result as a linear combination of W. The coefficients become the jth column, okay, of the matrix representation. So the coefficients become the jth column of the matrix representation. Kernel or null space of a transformation. The kernel of a linear transformation Tv to W is the set of all vectors in V that get mapped to the zero vector in W. Okay, it is the set of all vectors in V that get mapped into the zero vector in W. So kernel of T is equal to V within V, where the transformation of V is equal to 0. It is always a subspace of V. If ker T is equal to 0, okay, so ker T is 0, the transformation is injective, or it means it is 1-to-1, okay, 1-to-1 mapping. Image or range of a transformation. The image or range of a transformation is the set of all possible outputs of T, okay? So image of T is equal to TV. Transformation of V, V within capital V, okay, it's included within W. It is always a subspace of W. The dimension of the image is called the rank of T. We've seen that before. So the dimension of the image is called the rank of the transformation. Again, the image is the set of all possible outputs of T, or possible results. Meanwhile, the kernel is the set of all vectors that get mapped to zero vector in W. Connection with matrices. If T, the transformation, is actually a transition from Rn to Rm, being represented by a matrix A, kernel of T is null A, equal null A, is equal to x within Rn for Ax equal 0. It is the solution of Ax equal 0. Image of T is equal to the column of A, common space of matrix A. Let T be the transformation from R3 to R2, and Txyz equal to x plus y, y plus z. At first, let us establish the matrix form. Okay? Then you solve the kernel, or you get the kernel by solving Ax equals 0. And finally, you get the image, which is the column space of A. how to get the matrix form. Matrix form is given by 1, 1, 0, 0, 1, 1, and here is y. Okay, so you see each one of these arguments here become one row within this matrix. So the first row is x plus y, second row is y plus z. Okay, how does x plus y become 1, 1, 0? Okay, so you need to establish that each column is actually belonging to one variable, one unknown. Okay, so x, y, z, correct? Now, for the first row, it is x plus y. So x exists and it's multiplied by 1. Y exists multiplied by 1, but z is 0. Okay? For the second row, x is equal to 0, y equal to 1, and z is equal to 1. So 0, 1, 1. And this is the matrix 1, 1, 0, 0, 1, 1. Now, solve ax is equal to 0. We simply multiply it by x, yeah, like x1, x2 if you want, okay, or actually not x1, x2, x3, but rather x, y, z, since we have three variables. So you get 1, 1, 0, 0, 1, 1 multiplied by x, y, z is equal to 0, 0. The equations are x plus y equals 0, y plus z is equal to 0, which we already have, okay? So, which give us s is equal to minus y and z is equal to minus y. We solve them all in respect of y, and you can consider, or you can take y equal to 1, okay? So we fix y at 1, and we get x and z in respect of y. So curl of t is, okay, x, which is minus y, and y being the parameter, we take y equal t, okay? And as a fixed value, y equal 1. So curl of t is equal to, okay, x is equal minus y, which is minus t. Then y is equal t, okay, and z is equal to minus y, which is minus t again, with t within r. So the span is, or curl of t is the span of minus 1 for t equal 1, okay, minus 1 plus 1 minus 1. And this is the kernel. Now, the dimension of the kernel, by the way, is 1 because we have only one solution, like one unique vector here. Now, the image, which is the column space of A, okay, so we consider these columns. This is the image, but we need to choose only the unique columns. So image of t equals span 1, 0, 1, 1, 0, 1, but notice the first two columns already span R2, okay? So you see 1, 1 doesn't fit. Why? Because it is the combination of 1, 0 plus 0, 1. So the image of t, the rank of t is, yeah, image of t is R2, not R3. And the rank is 2 because you have two bases, two generators, okay, two unique vectors. You see the middle one does not count here, the middle column. Why? Because if we add the first column to the third, you end up with the one in the middle. So it's the combination of the addition of the first and third column. Hence, the image of t is R2 and the rank is 2, not 3. Summary. The kernel is all the inputs that collapse to 0, which are the solution of ax equal 0. As simple as that. Image is all the possible outputs, which the set of unique columns within the matrix. And they connect through the rank nullity theorem. So the dimension of V should be equal to dimension of curl T, which is 1 in the previous example, plus dimension of the image of T. So if we go back to the previous example, you have the dimension of image of t is 2, dimension of curl of t is 1, 1 plus 2 equals 3, which gives us back the dimension of v. And this complies with the theorem, okay? So our evaluation is correct because, again, as a reminder, you have dimension of kernel of t equal to 1, because we've gotten here one unique vector. Dimension of image of T is equal to, which is the rank, in other words. If we add them together, okay, they are equal to 3. What is 3 is simply the dimension of the V space. Okay, let us go back to some concepts, and despite the fact that we might have repeated some of these, we might have already mentioned them, but it's okay to go back and to review in order to solidify them within our minds, okay, in order to solidify these mathematical concepts. So we start again with the kernel or null space. So let T be a transformation from V to W, a linear transformation. The kernel or null space of T is simply given by ker T equal V existing within the V space for T of V is equal to 0, which is the solution of AX equals 0. It's the set of all input vectors that are mapped to the 0 vector that render T of V equal 0, okay? It's the set of V's for which T of V is equal to 0. Now, it's always, the kernel is always a subspace of V. If ker T is equal to 0, then T is injective, okay? No solutions. So it maps 1 to 1. Image, okay, or range in other space. The image of T is given by image of T equal T of V for V existing in V included in W. It's the set of all outputs of the transformation or the set of columns that are unique within the matrix. It's always a subspace of W. The dimension of the image is called the rank of T. And again, as a reminder, dim of ker T plus dim of image of T, which is the rank of T, okay, as we've seen in the previous example, it was 1 plus 2. It gives us the dimension of V, which is 3 in the previous example. Matrix connection, if T is represented by a matrix A, okay, ker of T is equal to null of A, so it is the solution of AX equals 0. Image of T is equal to the columns of A, the column space of A, only for the columns that are unique. So, as an example, you have T, R3, R2, T, X, Y, Z, X plus Y, Y plus Z. We've seen it just before this example. Matrix form is 1, 1, 0, 0, 1, 1, because you have X plus Y and Z equals 0. And the second, you have 0 and X, 0 for X, Y and Z are 1. The kernel, okay, you solve AX equals 0. So X plus Y equals 0, Y plus Z is equal to 0. You get X equal minus Y and Z equal minus Y. So we need to fix Y, okay? Or to parameterize Y. So ker of T, let us suppose Y equal T. So, because again, we have 3 variables but 2 equations, correct? So, X, Y, Z becomes, okay, for X, you replace it by minus Y, which is minus T. For Y, it is T already. And for Z, which is equal to minus Y, it's replaced by minus T. And we assume that, like, we let T be 1. So, ker T is equal to the span of minus 1 plus 1 minus 1. The dimension of ker T is equal to 1. Now, as for the image, okay, you go back to the matrix and we pull up the different columns. It is the span 1, 0, 1, 1, and 0, 1. That's the image of T, but the first 2 columns already span R2. Okay, so 1, 1 does not count. Why? Because you have, again, 1, 1 is a combination of the first column added to the third column. So it cannot be counted in. Or you can take the first 2 columns, which is 1, 0, 1, 1. Okay, these are two. These two are also unique. So the span, okay, image of t is equal to R2, and the dimension of mt is equal to, dimension of curve t is equal to 1. 1 plus 2 is equal to 3, which gives us back the dimension for the V space. Another exercise, let t be the transformation from R4 to R4, given by t, x1, x2, x3, x4, having 4 parameters, 4 variables, equal x1 plus x2, x2 plus x3, x3 plus x4, x1 minus x4. So we can notice you will have 4 rows within the matrix, okay? And you can pause the video and try to solve it, to form the matrix at first, then you get the kernel, which is the solution for ax equals 0, x being the kernel, of course, the unique solution for that equation, and then find out the image and the rank of this transformation. After that, you add it to the kernel, you verify if it will be 4, okay, which is the dimension for the transformation, for the space, I'm sorry. Okay, let us start to create the matrix at first. So A is equal to, you have on the first row, x1 plus x2. So x1 and x2, the first two variables are 1, and the rest, which are x3 and x4, are 0. Okay. Then for the second row, you have x2 and x3 are 1. So x2 and x3 are 1, but x4 is not available and x1 is not available, so they are 0. Third row, x3 plus x4. So 1, 2, 3, and 4. Here you have 1s, and elsewhere you only have 0. Okay, the last row, which is x1 minus x4, so x1 is 1 and x4 is minus 1, and the rest is 0. Okay, in order to simplify it, to simplify this, actually to get the basis, you need to run the row reduction, the RREF. Okay, so how to reduce the rows? Let us start by eliminating 0 from the last row, which is row 4. Okay, so R4 is equal to R4 minus R1. You simply evaluate R4 minus R1, which is 1, 0, 0, minus 1. And you have minus R1, which is minus 1. Minus 1, that's the row 1, by the way. Okay, 0, 0. You add them together. So 1 minus 1, 0, minus 1, 0, minus 1. And you place them at row 4. Then we need to eliminate this minus 1 here in row 4, okay? So that it would be triangularized. This is how we are executing or running a row reduction. It needs to become a triangular matrix, okay? Upper triangular one with all the elements beneath the diagonal becoming 0. Okay, so R4 is equal to R4 plus R2. Okay, so this is R4 minus 1, 0, minus 1 plus R2. Why? Because it's the only, yeah, this line has 1 here and has 0 here. So when we add to it, okay, we can eliminate this minus 1 and it will become 0. So, and since you have already 0 here, if we add them together, you won't re-establish a non-zero value at the first element of this row. Okay, so you have 0, 1, 1, 0. 0, 1, 1, 0. You add them together, so you get 0, 0, 1, minus 1. 0, 0, 1, minus 1. Okay, now let us get rid of this value here and render it 0. Okay, so R4 is equal to R4 minus R3. Okay, let's get back. R4 is equal to R4 minus R3. So this is row 3. This is row 4. Okay. So 0, 0, 1 minus 1. that's row 4, and row 3 you have, okay, minus R3, so 0, 0, minus 1, minus 1. So you end up with 0, 0, 0, and minus 2. Let us check it out. Okay, 0, 0, 0, minus 2, and it became a triangular matrix, okay? Which is exactly what we wanted. Now, we have determinant of A, we can evaluate it, is equal to what? Equal to, yeah, you can evaluate the determinant using this method. Okay, so you start from here, minus 2, and let me clear it out. Okay, it would be easier. Okay, so you start with minus 2 here. Okay, and you evaluate the determinant of this. Okay, which is, so you have minus 2 multiplied by, okay, you take the first element and you bar the intersecting rows and columns. So it is 1 multiplied by 1 minus 0, okay, which is equal to minus 2, different than 0, so A is invertible, okay, and hence the rank of A is equal to 4, okay, the rank is equal to 4, and the nullity is 0. Now you might ask, why is the rank 4? Okay, notice how many pivots we have. One is the first pivot, then another pivot, each one at the right side of the pivot above it, or in the above row. You have zeros underneath each pivot, and you have unique vectors, of which you don't have like a vector that is a combination of the other vectors. So we can deduce that the rank is 4 and nullity is 0. Let's find the kernel of T. Okay, ker T is x within R4, ax equals 0, or in other words, the solution for ax equal 0. It is the set of vectors for which ax becomes 0. We want the solutions of the following equations. In other words, the set of equations are x1 plus x2 is equal to 0. That's the first one. x2 plus x3 equals 0. x3 plus x4 equals 0. And finally, x1 minus x4 equal 0. 4 equations. And by the way, another way to write this system of equations is to say ax equals 0. If you multiply the original matrix, with x, which is x1, x2, x3, x4, you get this system of equations. Okay, with x1, x2, x3, x4 being written in column format like that. You multiply it by a, you get the system of equations. So x1 is equal to minus x2, x2 is equal to minus x3. We are transferring x3 like the right side of each equation, the right side or behind or before the equality. We are moving it to the right of the equality from left to right. x3 is equal to minus x4, and x1 is equal to x4. Okay, now you replace x4. Yeah, you start replacing them. So x1 is equal to minus x2 equal to x3 plus x3 equal to minus x4, with x1 is equal to x4. So you have x1 equal to x4 and x1 equal to minus x4, 2x4, okay, is equal to 0. So x1 is equal to x4, 2x4 is equal to 0, hence x4 is equal to 0 by replacement. So ker of T, because if you replace x4 here, so you get x1 is equal to 0, x2, which is equal to minus x1, is 0, x3 is 0, and everything else becomes 0. So ker of T is equal to 0 vector, which means that the dimension of ker T becomes 0. This is the nullity value. The image of T, which is R4, the basis is the 4 columns again. So this is the basis 1 0 0 1 1 1 0 0 0 1 1 0 0 0 1 minus 1, and by using the row reduction, method, we have proven that these are 4 bases, 4 unique vectors, okay? Because we've gotten 4 pivots. Under each of them, you had like 0. So it became an upper triangular matrix, as we mentioned. So you had, for example, here it's a pivot, and the one above it is to its left. So it's each pivot is to the right side of the one above it, and underneath each pivot, not within this matrix, but within the one that we've row reduced. So under each pivot, you have zeros. So you have 4 bases, 4 columns as a basis. Hence, the rank is 4. Let's evaluate the rank nullity check, which is equal to the rank plus nullity equal to 4, because the rank is 4, which is the dimension of image of T, plus nullity, which is dimension of curl of T. Okay, the kernel is 0, as we've seen. So 4 plus 0 equal 4. It passes. It is correct. Why? Because 4 is the dimension of the V space. Another one, let A be equal to 1, 1, 0, 2, 2, 0, 0, 0, 3, and T of x is equal to AX. Let us find the rank, the nullity, or like the kernel and the dimension of the kernel of T. The rank of T. Let us find out the bases, all of that. Okay, so you can pause the video and try to solve it first. So let us find the image, dimension of the image, which in other words would be the rank for this matrix, okay, or the number of unique vectors, unique columns, so to speak. Dimension, and actually the kernel of A, which is the solution for AX equals 0, and the dimension for that kernel. In other words, it's called nullity. So dimension of ker T is, in other words, the nullity. As for the rank, it is the dimension of the image of T. Okay. Now, the columns are 1 to 0, 1 to 0, and 0, 0, 3. Okay? The first two are linearly dependent, because simply they are the same. You can say, in other words, the second one is a combination of the first one, and vice versa. So the distinct ones are 1 to 0 and 0, 0, 3. Hence, the image of T is equal to span. You open the 2 curly brackets, and on the inside, you insert the 2 distinct columns, which form the bases, by the way. And these are 1 to 0, 0, 0, 3. So the rank is equal to. Now, the kernel is given by AX equals 0, so x1 plus x2 equals 0, okay, which is x1 plus x2 equals 0. Then 2x1 plus 2x2 equal 0. 3x3 is equal to 0. We simply multiplied the matrix 1, 2, 0, 1, 2, 0, 0, 0, 3 by the column vector of the variables, which are x1, x2, and x3. So you multiply row by column, as you remember, which is x1 times 1 plus x2 times 1 plus x3 times 0, which is 0. So this is AX equals 0. You have x1 plus x2 equals 0. Then you have, for the second row, 2x1 plus 2x2 equals 0. Let me rewrite the first equation. x1 plus x2 is equal to 0. Finally, you have 3x3 equal 0. So let us find the kernel. Let's assume x1 equal to 1. If x1 is equal to 1, then x2, which is minus x1, would be minus 1. And x3 is already given as 0. So the kernel of T is the span 1 minus 1, 0. Hence, the dimension of curl of T is equal to 1, because we only have one vector. That would be called the nullity, the dimension of curl T. So the dimensions are dimension of the image of T, which is the rank or the number of distinct columns, 2, plus dimension of curl T, which is 1. Okay, one unique vector. So both of them added is equal to 3, which is the dimension for the V space, which is 3 by 3 matrix. So again, rank equal to, which is actually the dimension of image T, and the nullity is the dimension of kernel of T. Let T, the transform, be a transformation from U to V, and S be a transformation from V to W. So these are two linear transformations. Okay, the composition of S and T is the mapping SOT, okay, which gives us a transformation from U all the way to W, okay, passing through V. So T being the transform from U space to V space, S transform from V to W. So SOT, or composition of S and T, is the mapping from U to W, defined by SOT. U is equal to S times T of U, okay? So mapping from T to S at U is equal to, or at vector U is equal to S of T of U, the mapping of T of U. So proving if a composition is linear for vectors U1, U2 within U and scalar C. Let us check the additivity if it applies. So SOT U1 plus U2 is S of T U1 plus U2 is equal to S of T U1 plus U2, or S of T U1 plus T U2, S on the outside, okay? Also, it can be rewritten as STU1 plus STU2. The homogeneity, and sorry for this being ambiguous, but you will check it, you will understand it better as we use demonstrations in examples. Homogeneity, okay, how it can be homogeneous. So SOT CU is equal to S of TCU equal S of CTU, okay? So it is interchangeable. Thus, SOT is also a linear transformation. Matrix representation, suppose Rn is being transformed into Rm with matrix AMN, Rm to Rp with matrix BPM, then the composition SOT gives us R of n transferring to R of p is represented by SOT BA, okay, being transformed to B times A. So it is the multiplication of B with A. So suppose you have T Rn to n Rm with matrix AMN, Rm to Rp with matrix BPM, P number of rows, M number of columns. Then the composition SOT Rn to Rp is represented by B times A, which is B matrix multiplied by A matrix. Notice the order. So SOTX is equal to B multiplied by AX equal BA multiplied by X. Okay? Which means it respects the scalability or the homogeneity rather. Okay. So as an example, which will make the matter clearer, you have T, which is a transformation from R2 to R2, given by Txy equal to Xy S R2 to R2, which is Xxy given by X plus Y plus Z. Try to resolve this example and we will go to the solution in a moment. Now you can pause the video if you want to solve it first, to try to solve it before getting back to the solution. But mind you, and here's a side note, like a disclaimer, so to speak, Sxy was written in a wrong way. So it is given by X plus Y plus Z as a first argument and Y as a second argument. Okay? So we need to pay attention to that. Now let's get back to the solution. So matrix of T is given by, okay, you have Txy is equal to X, okay, and Y is 0 in the first row or the first element. Then next to it is Y without X, so X is 0 in the second element. In other words, you have, it can be rewritten, Txy is equal to 2x plus 0 times y and 0 times x plus y. Okay, so you have 2 plus 0, 2x plus 0y, which is 2, 0, that's the first row, and 0x plus y, so 0, 1. That's the second row. As for the matrix of S, it's given by, okay, x and y are 1 for the first element, so 1, 1 is the first row. This is for S. Then you have for the second row, y is multiplied by 1, but x is 0, so 0, 1. Okay, what is the composition? Let us find the mapping of t over x, so SOT xy is given by S of 2x y, okay? This is what SOT or S of t, okay? So you replace x by 2x and y by y. So we are mapping t into S, okay, which is given by S to x y, which gives you, okay, you replace x by 2x and y by y, okay? This gives us, again here, I think, yeah, there is no z, you have x plus y and y, so x plus y in the first argument is replaced by, x is replaced by 2x, okay, so you get 2x plus y, y remains the same. As for the second argument, which is y, okay, you don't have x here, you simply have y, so SOT or S of t is equal to 2x plus y, y. Let's talk about the change of basis. First of all, what is the motivation behind it? A basis is a coordinate system for a vector space. The same vector, like axes x, y, z, are three bases or form the basis of a 3D axis system, okay? And they are three unique vectors that are linearly independent. All right, so a basis is a coordinate system for a vector space. The same vector or linear transformation can look very different when expressed in different bases. Changing basis means expressing vectors in a new coordinate system, adjusting the matrix representation of a linear transformation accordingly based on this new coordinate system. Okay, change of basis for vectors. Suppose V is an n-dimensional vector space. The old basis is B equal B1 all the way to B2. New basis is C, C1 to C2. If a vector, lowercase v, is within a V space, having coordinates of VB in basis B and coordinates of VC in basis C, then V of C is equal to, so this is how we transfer from one coordinate system to the other. V of C is equal to P minus 1, okay, which is the inverse of the P vector, and we will see it in an example, multiplied by V of B. Okay. So what is P? P is actually the change of basis matrix from C to B. Columns of P are the new basis vectors expressed in the old basis. We're gonna check this out. So change of basis for linear transformation. Suppose T is transformation of V into V is a linear transformation. In basis B, its matrix is A. In basis C, its matrix is A prime. So the relationship is A prime, okay? So the new matrix in the new coordination system is given by P minus 1, the inverse of P, multiplied by A, okay, the matrix in the old basis, times P, which is again, okay, the matrix of the change of basis, where P is the change of basis matrix as above. So this process is called a similarity transformation, and we're going to apply that in the upcoming examples. Example, let T be the transformation from R2 to R2, with T of xy is equal to x plus y, x plus 3y. In the standard basis, so what are the two rows? What is the matrix? It is simply the set of rows formed by the different elements within this transformation. So 2x plus y is simply 2 plus 1, okay? 2, 1 within the first row. As for the second row, you have x plus 3y, so x is multiplied by 1. y multiplied by 3. So it is 2, 1, 1, 3. In other words, if we multiply a with x, which is 2, 1, 1, 3 multiplied by x and y, you recover the original form of t, which is the transformation. Okay? You recover t, x, y, which becomes this set of equations. Okay? So it is another way to write the form. Now, to write the transformation. So choose a new basis C. Okay, let us choose a new basis. Let's say the new basis is C1 is equal to 1, 1. C2 is 1 minus 1. Then the change of basis matrix is, okay, what is the change of basis matrix? It is C1 and C2 placed as columns. Okay, this is the change of basis matrix, the change from one coordinating system to another, or coordinate system to another. So let's say that this coordinate system is beta or B. We are transferring from B to C, where C is given by C1, 1, 1, C2, 1 minus 1. So you place C1 in the first column, C2 in the second column, and this will form the P matrix, which is the matrix of the change of basis, or change of basis matrix. Okay, now what would become of A when it changes the basis or the coordinate system? So A prime would be equal to P minus 1, which is the inverse of P, multiplied by A, multiplied by P. Okay, let us at first evaluate P minus 1, which is the inverse of P. So let's consider you have a matrix D, okay, given by A, B, C, D. Okay, to remind you on how we get the inverse of a matrix. So what you have is D minus 1, which is the inverse, would be equal to 1 over the determinant of D, that of D, which is AD minus BC, multiplied by, we swap D and A, so you have D, A, and you multiply B and C by minus sign without changing their locations, and this is how you get the inverse matrix. So in such case, P minus 1 is 1 divided by minus 2, okay, which is minus 2, minus 1, or minus 2, multiplied by, you interchange 1 and minus 1 here, so minus 1, 1, and you multiply B and C with minus, so minus 1, minus 1, and the final answer would be 1/2, 1/2, minus 1/2, and 1/2, 1/2, and minus 1/2. Okay, so this is P minus 1. You multiply it by A and P. Okay, you multiply it by A times P, and you get finally A prime, which is the projection, or like the image of this matrix on a new coordinate system. Okay, so let's say you have a basis T epsilon equal A given by 4, 1, 2, 3, and the basis is B given, okay, by B1, 1, 1, B2, 1 minus 1. So I need to find the matrix of linear transformation in respect to the basis B. So this needs to be transformed or transferred from epsilon basis, which was the original coordinate system, to B basis, which is given by B1, 1, 1, and B2 equal 1 minus 1. You can pause the video to try to solve it first. then you can get back to the solution. So let's keep moving. We need to form at first the P matrix. Of course, again, the formula is for A to get the A transform, okay, or like the value of A within the new coordinate system. This is equal to P minus 1, which is the inverse of P, multiplied by A multiplied by P. Okay, at first P is given by the set of B1 and B2 placed as columns. This is the new coordinate, the change basis, okay, which is 1, 1, 1 minus 1. P minus 1 is equal to 1 over that of P, which is minus 1 or minus 2, multiplied by minus 1 minus 1 minus 1, 1, okay, which is, we flip 1 and minus 1 here, okay, so we swapped them basically, and you multiply by minus 1 this diagonal here, minus 1, which is equal to 1 divided by minus 2, so 1 half, 1 half, 1 half, minus 1 half. Okay, P minus 1 times A, so you multiply that by A, we get, okay, so this is 1 half times 4 plus 1 half times 2. I won't multiply all of it, okay, but this row multiplied by this column will give us A11, which is the value of the element at the first row, first column, which is 4 times 1 half, or 4 divided by 2, plus 2 times 1 half, 2 divided by 2. So it is 2 plus 1, which is 3. Okay, and this is 3. Now let us see, check like this one here. So it is given by 1 half times 1/3 plus 1 half times 3. I'm sorry, 1 half times 1 plus 1 half times 3. So 1 half plus 3 divided by 2, or 4 divided by 2, which is 2. So this is the result here. Let's clear it a little bit. Now, as for this element, which is the second row, first column, or A2, 1. It's equal to 4 times 1 half, or 4 divided by 2, plus 2 times minus 1 half, or minus 2 divided by 2, or minus 1. So 2 minus 1 is equal to 1. And this is the value here, okay? At the second row, first column. The same thing for the remaining value within the matrix, which is this multiplied by this. Okay, so 1 half minus 3 divided by 2, which is minus 2 divided by 2, or minus 1. Okay, let us continue. So P minus 1A, we've gotten the answer here, which is 3, 2, 1, minus 1. We multiplied again by P, the original P matrix, and you get 5, 1, 0, 2. This is the transform of the A matrix from the epsilon basis to the B basis. This is the final answer. This is what the matrix would look like in the new coordinate system. So, transform of A into the B coordinate system gives us P minus 1 multiplied by AP equal to 5, 1, 0, 2. That's the final answer. Okay, another one. You have two bases here, or two coordinate systems. Basis B given by B1, 1, 2, B2, 3, 1. Basis C, another coordinate system, given by C1 equal to 1 and C2 minus 1, 1. And VB is equal to minus 1. Okay, so this vector within the B system is given by 2 minus 1. I need to find its image, or what it would look like in the C coordinate system. So I need to transfer it from this coordinate system and to see its values when they are measured in respect of the other coordinate system. Okay, in other words, to make it a little bit simple, what we're doing here is like you have a point here being defined on this xy coordinate system, but we've changed the location of the axis to be like this. Okay, this is the transfer of the coordinate system. So what would that point look like here? What would be its own values? Okay, so it would be like minus 10, for example, here at the x-axis, and like 10 plus 10 at the y-axis level. Okay, meanwhile, on the first or original coordinate system, it was 2 by 5, let's say. Okay, this is what we're talking about. This is what we are trying to do, to transfer VB from the B coordinate system to the C coordinate system. Okay, let us start at first with the matrix for B. So we have PB is given by 1, 2. You place B1 and B2 as the columns of the matrix. So 1, 2, 3, 1. PC is given by 2, 1, minus 1, 1. Okay, so C1 and C2 become the columns for the P matrix, okay, at the basis of C. Now, P minus 1, which is the inverse, because we are transferring from the B basis to the C basis, okay? So the P matrix of the C basis is the one that is relevant here. P minus 1C, which is the inverse of PC, is given by 1 over that of P, which is 2, minus 1 plus 1, so 2 plus 1, 3, so 1 divided by 3. You swap 2 and 1, so they become 1 and 2. We've swapped them, we interchanged them. Then you multiply this diagonal by minus, so you get minus 1 plus 1 from the lower one, from the lower left to the upper right. Okay, so we inverted the signs of this diagonal basically. Minus 1 becomes plus 1 and plus 1 becomes minus 1. Clear? As for this diagonal, we've flipped or swapped the value. So 2 was exchanged by 1. Okay, so what we get is 1/3, 1/3, minus 1/3, 2/3. This is the inverse of the P matrix. Now, V of C is given by, so the value of the matrix, which was defined on the B coordinate system, becomes P minus 1C, which is this one, multiplied by the matrix here, by VB, multiplied by PB, okay? Or like you can, you can change the order. So let's check P minus 1 times PB. Okay, PB is the original system, the original matrix, by the way, the original axis system, the original transformation. P minus 1 multiplied by PB is 1/3 minus 1/3, 1/3, 2/3, multiplied by 1, 3, 2, 1, which gives us 1, 4, 3, 1 minus 1/3. Okay. And then this answer you multiply it by the matrix itself, or the vector in such case that is changing base. So 1, 4/3, 1 minus 1/3, multiplied by 2 minus 1. It gives us 2 plus 8 divided by 3. 2 minus 4 divided by 3, which is 2/3, and then you multiply 1 by 2 and minus 1/3 by minus 1, so 2 plus 1/3, okay, which is 7 divided by 3. So VC is given by PC minus 1 times PB times PB, okay, so the transpose of the matrix of the change of bases multiplied by the matrix of the original bases, which is PB in this case, multiplied by VB, which is the matrix that is, or the vector that's changing base, okay, the one that is being projected from another, from one coordinate system to another, which gives us 2/3 by 7, 3. Okay, and this is the answer. So vector v that is defined on the coordinate system on the first basis b, which is given by 2 minus 1, becomes at the second coordinate system defined by c1 2 1 and c2 minus 1 1, it becomes 2/3 7 divided by 3. So again, what we've done is we got the transpose of p for the c basis, we multiply it by the original base, which is pb, then we multiply it by vb, and we've gotten the new value for that matrix at the new coordinate system. Another exercise, you have the following two linear transformations, t1 from R2 to R2 given by t1 equal a equal to 0, 1, 3, t2 given by b equal 4, 1, minus 2, 5. So let t be equal to t1 o t2. So we are mapping the two transformations together. We need to find t, then find t of v, transform of v equal t2 of t1 of v, applied to vector v with v equal 1, 2. So you can pause, try it yourself at first before coming back to the solution. Now, starting from 1, so t is equal to t2 o t1, okay, which is b times a, okay, b times a, or 4, 1 minus 2, 5, multiplied by 2, 0, 1, 3, which gives us, okay, so this was supposed to be t2 o t1, okay, so it's the inverse. Okay, perhaps the question was wrong to begin with. So t equal t2 o t1, we multiply b of t2 by a, which is, okay, 4, 1 minus 2, 5 times 2, 0, 1, 3, so 8 plus 1, 9. Then you have 4 times 0 plus 3, okay, so 3. You have minus 2, 5 multiplied by 2, 1, so minus 2 times 2, minus 4 plus 5, so plus 1. And finally, you have 0, 3 multiplied by minus 2, 5, 0 times 2, minus 2, 0, and 3 times 5, 15, so 15, okay, 9, 3, 1, 15. Now, as for the second, so this is the projection, okay, or the image of T2 and with T1. Apply T to vector V, so T of V is T times V, which is, this is the transform 9, 3, 1, 15. You multiply it by the vector V here, which is 1, 2. So 9, 3, 1, 2 is 9 times 1 plus 3 times 2, which is 9 plus 6 or 15. And 115 multiplied by 1, 2 is 1 plus 30, so 31. This is the T applied to vector V.